Wani. Very welcome, big welcome to everybody for this webinar, another one in our series during the lockdown period in South Africa. Today we have the privilege to welcome Dr. Leon Krüger from Mintex, where he is the hydrometallurgy manager. I have worked with Leon for over 7 years as a colleague, and we have had many interesting interactions with him. He's an excellent speaker in this area and has a depth of knowledge about industry. He's worked in a wide variety of industrial applications. He's worked in diamonds and has a history, and he's even worked in equipment supply. So his perspectives on the industry is invaluable. So Leon, you can start loading your presentation. Just for the attendees, we have Leon's permission to distribute the presentation after the webinar today. So all registered attendees are welcome to a copy. And then while Leon is talking, if any questions come to mind, you can use the Q&A tab at the bottom of your screen to post a number of questions. And at the end of the discussion, we will have a short Q&A session where I will curate and interact about the questions and make sure that we get some answers. So without further ado, I'm going to say welcome to Leon. Leon, you can start your presentation when you're ready. We're very excited to learn all about why rare earths are special and so difficult to process. Thank you very much.
Good morning, ladies and gentlemen. My name is Leon Krüger, and I'm a hydrometallurgist working at Mintex. I've had a relationship with rare earths since my days at university, and over the 30 years since then, it's been a bit of a roller coaster. Rare earths have been up and they've been down. Luckily, I'm happy to say that I think we're on another upward trajectory, and hopefully South Africa is ready to join this ride. My talk today is really about the characteristics of rare earths and why they are so special. Through the years, many people have been perplexed by the rare earths, and perhaps none so than Sir William Crookes. He said, the rare earths elements perplexes us in our researches, baffle us in our speculations, and haunt us in our very dreams. They stretch like an unknown sea before us, mocking, mystifying, and murmuring strange revelations and possibilities. Very eloquent indeed, and so it's clear that even from the early days, 100 years ago or more, people were fascinated by what rare earths can offer us from a technological perspective. At the same time, my experience has always been, if something is really great, there's often a bit of a dark side to that. And as we metallurgists know, we've discovered the hard way over the years that the rare earths are also very difficult to process. So my aim this morning is to try and shed a little bit of light on exactly what is it that makes the rare earth so special and why it is so difficult to process. Perhaps just start with a little bit of history, because the rare earths came about and then were almost forgotten. We're essentially forgotten for 100 years. In 1751, in a quarry near Bastnäs in Sweden, a reddish brown mineral was found that was very strange, not known at the time. Then 30 years essentially went by until Carl Arrhenius found another dense mineral near the town of Ytterby in Sweden. It was actually only a few years later that the Finnish chemist Johan Gadolin connected the dots and came to the conclusion that this mineral is a new mineral. And he regarded it as rare because nobody's heard about this before. And that's essentially where the name rare earth comes from. So, after that, for about 100 years, everybody had forgotten about these minerals until they came to the fore with their use in incandescent mantles in a lighting application. So, I think the first step to explore the reasons for why they're so special is perhaps to look at what they are. And here I would like to beg everyone's indulgence that I'm going to have to touch a bit on quantum chemistry to be able to explain properly the reasons for this. So if one looks at the periodic table, when we're all familiar with the periodic table, how the elements are arranged in groups and periods, but the rare earths are already showing that there is something special even on the periodic table. If one looks at where they are located, they are between barium and hafnium on the table, and they essentially stand out perpendicular to the table in our direction. So I suppose the question is, so what are they? Do they react like transition metals, or are they any different to what we know in the periodic table? IUPAC defines a transition metal as an element whose atom has a partly filled d subshell, or which can give rise to cations with an incomplete d subshell. So what we are used to as metallurgists is, if you move across a period like, say, the first series of transition metals, there are distinct changes that happens as you go along. For instance, the character of the bonding changes from very ionic on the left-hand side to much more covalent as you move across. So the question is, how do the rare earths react? And why would they be different? So first of all, we just have to take a step back and look at the Aufbau principle that describes how the elements are essentially formed. They are formed by adding electrons to available orbitals as one moves along. Every time a proton gets added to an atom, an electron is also added, and it's added to the lowest energy orbital. So, for example, scandium has the following electron configuration. As you move across, electrons are added to the d orbitals until you get to zinc, when all the d orbitals are full. So this is essentially how it happens as one moves along the periodic table. So to answer the question whether a rare earth is a transition metal, we have to follow the Aufbau process, and also consider the nature of the orbitals. So the first thing that I would like to mention is that orbitals are not containers containing electrons. They are really just defined as regions around the nucleus of an atom where it's likely to find an electron. So from quantum theory, a quantum mechanical model was developed to describe the orbitals in an atom. So just very briefly and very superficially, an orbital can actually be described and defined by a set of 4 quantum numbers. Quantum numbers are all integers, and they are very distinct numbers. The most important one, the first one, is the primary quantum number, n, which is really related to the energy of the electron. And as such, it describes how big such an orbital would be. The second quantum number is the angular momentum quantum number, and this describes the shape of the orbital. In other words, what the spatial orientation and the spatial distribution of the electron density would be. The magnetic quantum number m is really an indication of the orientation of the orbital, how it moves around when it's exposed to an external magnetic field. The last one is the spin quantum number, and it's also one of the most difficult ones that took a long time for people to get their heads around. It is really describes the magnetic field associated with an electron. So, taking into consideration these quantum numbers, let's just look at, for example, a d orbital. A d orbital, say the 3d orbitals are in the third shell. So the primary quantum number is 3 and the angular quantum number is 2. That is also the maximum of the third shell, because quantum theory also says that the angular momentum quantum number can only have a maximum of n minus 1. The angular quantum number is also important because it also determines the number of orbitals, according to that equation on the screen there. So that means we have 5 d orbitals. And on the left, I've got a picture of just roughly how one of the 3D orbitals might look like in terms of where the electron density can possibly be found. So if one follows the Aufbau principle then further, one eventually arrives at a point where the next electron has to occupy an orbital described by a principal quantum number of 4 and a maximum angular quantum number of 3. Since the d orbitals have an angular quantum number of 2, these new electrons will fill a new kind of orbital, an f orbital, characterized by an angular momentum quantum number of 3. Okay, so this also means that there will be more orbitals in this shell, because if you have an angular quantum number of 3, that means there are 7 f orbitals. Okay, so we have now a situation where the rare earths are starting to fill the f orbitals. The unusual thing about the f orbitals is that they have an angular momentum quantum number of 3, and there are also 7 of them. And this is going to prove quite important when one looks at why the f orbitals or the rare earths are so special. So just to answer the question that I posed earlier, following the IUPAC definition, the rare earths are not transition elements because they are really the result of filling of f orbitals. So they are therefore likely to react a little bit differently to what we are used to. So it's exactly this new angular momentum quantum number that proves to have such a profound impact on the characteristics of the 4f elements or rare earths. I said before, the angular momentum determines the shape of the orbital. Since this momentum is now so much higher, it means that it's likely to be much more complex shapes, and it also results in the fact that these orbitals are very directional, and therefore the electrons in them shield each other from the nuclear charge very, very poorly. If you see on the picture there on the left-hand side, the complicated shapes of the f orbitals. This sort of gives you already an idea of why they would have all these unique properties that we've come to associate with them. And also perhaps that the coordination could be different to what one is normally used to. The poor shielding also means that much of the electron density of the f orbitals are fairly close to the nucleus, as you can see by that graph on the right-hand side. So the f electrons are tended to be pulled closer towards the nucleus, and this is would also have a profound effect on the way that they react. So, to summarize, what is the impact of the f orbitals? Because a large part of the wave function is sort of pulled inside the xenon core, it means that the f electrons are not very available for bonding. And this also means that they are shielded pretty effectively from external electric fields, and that also has important impact. As we've also seen, there are now 7 orbitals, 7 f-orbitals. So that means one could have quite a large number of unpaired electrons in them, and that would result in a high magnetic moment. Another aspect to consider is that because of the nature of the f-orbitals, the orbital and spin angular momenta can couple much more strongly than in the case of the d orbitals. Now this means that the already large magnetic moment of these elements is even amplified even more. So from a high magnetic moment to a very large magnetic moment overall. And this coupling also leads to enormous magnetic anisotropy. Now this is also very important for the rare earths from a magnetic perspective, because magnetic anisotropy is related to the reluctance or reluctance of the direction of the magnetization to change when exposed to external influences. The poor splitting of the electronic states is a result of the fact that the f-orbitals are very well shielded from external electric fields. So this means that the electronic states are not split as widely as in the case of the d orbitals, and this leads to very, very narrow transition bands. In fact, these bands are so narrow that they are essentially completely line-like. Again, very different from the d elements where these tend to be quite broad. So if one can summarize all this, we have a larger number of f-orbitals, and there's also the nature of the f-orbitals. And this equals a unique chemical and physical behavior, certainly compared to that of the d elements that we are much more familiar with. This unique chemical and physical behavior, for instance, can translate into things such as unusual spectroscopic properties. As I've said before, the electronic transitions take place in very, very narrow bands, and this leads to very sharp spectral lines, absolutely line-like. Also, the large number of unpaired magnetic moments leads to a very large overall magnetic moment, which has large impacts in applications where magnetism is important. Also, the high magnetic anisotropy is again very important in applications where one needs strong magnetic forces reliably. And also the shape and the number of f-orbitals also leads to unusually high coordination numbers for complexes of rare earths. So all these things are unique and likely to be a result leading to the unique physical and chemical properties of the rare earths. So it's exactly these unique properties that have led to an enormous number of even game-changing, often technical and industrial applications. For instance, one can essentially divide these applications into two broad groups. The one is the rare earths as process enablers. Its examples of these are their use as catalysts in oil refining or emission control systems. Also, they can be added to metallurgical systems to refine the metallurgical structures, and also in glasses and in the ceramics industry to change the properties of these glasses. And an extremely exciting application is the therapeutic applications in medicine, where one of the rare earths are used in fighting cancer. But rare earths can also use on their own in their compounds as technology building blocks. For instance, in electric motors, permanent magnet electric motors, for EVs or power generation. They also play key roles in spectral applications such as lasers, filters, and lenses. So they have an enormous number of technological applications, but I would just like to highlight two of these and link them to some of these special characteristics of the rare earth elements. The first one is their really unique spectral characteristics. As I've said before, the very narrow transition bands that their compounds exhibit. And one of these applications making use of these characteristics are lasers. Lasers have become such a part of our world and has really often changed our lives in many ways. If one takes a compound made of rare earths like the neodymium YAG crystal, and you excite that up to upper excitation band levels, as these electrons then relax to the lower fields, because of these small differences in the electronic in the energy fields, energy levels, they then emit extremely narrow lines of emission. For example, this neodymium YAG laser emits at 1064 nanometers. And as you can see there on the picture, it is absolutely needle-like. Now, this is extremely important and useful for application in, for instance, lasers. And this enabled lasers to be used in such a wide range of applications, from medical to military to industrial and commercial applications. In the military applications, lasers have actually been used in the as the death rays that are commonly that used to be common in cartoons. This is made possible by rare earths. Also things like skin treatments, dentistry, and as well as surgery. For instance, these lasers can be used very effectively for soft tissue ablation and at the same time coagulation. So as you can see, how one special characteristic can have an enormous impact on our lives. The second special characteristic of rare earth compounds are the magnetic characteristics. As we've seen, they have huge magnetic moments and enormous magnetic anisotropies. Now, in modern applications, there are a number of things that one needs from a magnet. The first thing we need is very large coercive forces, because the larger the coercive forces, the smaller we can make the device. Magnetic materials should also be reliable. They shouldn't lose their magnetization. So therefore, the anisotropies should also be very high. Now, this is exactly what rare earth-based magnets provide. For example, if you look at the table there, the neodymium iron boron magnet, rare earth magnet, essentially has an energy product of an order of magnitude higher than the normal ferrite magnets that we know. So this is clear that this gives us something very special to work with when we do technological developments. So what we can say is, due to the high coercivity, these rare earth magnets are extremely efficient to convert electrical energy to mechanical energy, or the opposite way around. A specific example of the use of these special magnetic properties is in electric vehicles. We've seen that this is really a topic that is going to take off, and I was always thinking that I'm probably driving my last internal combustion engine car, at the speed at which electric vehicles are taking off. Dr. Niels Beckerberg of Roskilde has described this movement as that rare earths are really the engine of electrification in our lives. He says, because without an electric motor, an EV is just an expensive battery on wheels. So once again, pointing out to the importance of rare earths in the new electric mobility that is taking place around us today. The beauty of these rare earth permanent magnet motors in the automotive application is really that it provides all these feelings that we got to know in internal combustion engines. It can operate over a broad speed range. It's got constant power delivery, high torque for rapid acceleration, and it's also reliable and robust. So it's actually a perfect replacement for the internal combustion engine. I guess the only thing that I will miss certainly is that beautiful mechanical sound of an internal combustion engine, but I guess one cannot have it all. So just to summarize this part, it's really thanks to the f-orbitals that rare earth compounds have such unique properties, and therefore offer these exceptional opportunities for game-changing technical innovation. And I believe this is what makes them truly special. But at the same time, the very f-orbitals that make them so special also make them very difficult from a metallurgical perspective. So let's just look at the chemistry of the rare earths and how it would impact on metallurgists when it comes down to processing these elements. If you consider again the electronic structure of, say, neodymium, we can see that the two s electrons can be removed relatively easily from the atom. The reason for this is that s electrons are really not shielded very well. And therefore, they don't experience the force of the nucleus very much, and they can be removed relatively simply. The further one, if one of the f electrons can also be removed, but once that happens, the poor shielding of the f orbitals results in the remaining ones experiencing huge attraction forces from the nucleus. And this means that the rest of the f orbitals are then even pulled further closer towards the nucleus. And that means that further removal of f orbitals becomes virtually impossible under normal coordination conditions. And therefore, it results in an unusual stability of the +3 valence state, almost exclusively. A further interesting aspect of the poor shielding of f electrons is that as one moves across the series, as you add more electrons and more protons to the atom, these electrons experience more and more of the nuclear charge. And this means that the electron cloud shrinks as one moves across the series. And this results in a steady decrease in the size of the rare earth ions as the atomic number increases. This is really the opposite of what we normally experience in the d block of elements. But another interesting thing is that even though they change in size, this is not a huge effect, and it means as you go across the series that the ionic radii remains relatively similar in size. Now this has quite an impact on the chemistry of the rare earths. In the first place, the interactions are highly ionic because of this prevalence for the +3, the valence state. It's almost exclusively in the 3+3 valence state, and the ionic radii are relatively similar. So what this means is if you take a similar ionic radius and the same valence state, it means you would expect the same chemical behavior. And if you have the same chemical behavior of all the rare earth elements, that means it will be very difficult to separate them from each other. And that is also indeed the case. And that probably prompted Mariano to say in 1989 that none of the rare earths are as rare as gold, but the extraction as pure elements requires a technology much higher than that for the winning of gold. Fortunately, nature does provide us with some assistance when it comes to the processing of rare earths, even though their chemistry is so similar. In the first place, we have promethium. This is a short-lived radioactive element that is not found freely in nature. So that gives us a handy break between ruthenium and samarium when it comes to a separation effort. Second one is that cerium and europium, one can actually manipulate the oxidation states, which gives us two more gaps in the series. And the third one is, because of the contraction of the lanthanides, we see that the electronegativity increases as we go down the series, and also the Lewis acidity increases down that line. So that gives us another tool to play with to separate these elements from each other. So if one then designs an extractant like PC88, which can make use of this difference in Lewis acidity, it just gives us some prospects for separating the rare earths. So if one can control the pH of such a system, it gives us an opportunity to separate the rare earths from each other, even though the chemistries are so similar. But I have to stress that the separation, the differences in the reaction to coordination with this extractant is still fairly small. So just to present a quick potential separation scheme using pH and redox, we can take our rare earth liquor, precipitate the rare earths as a hydroxide. The lights would precipitate, the rare earths would stay in solution. Then we could do some oxidative drying of the lights. It would oxidize the cerium, and then when we dissolve, the cerium will not dissolve, and we have therefore separated lanthanum and cerium from each other. Then one could do a pH-controlled SX process, which would then again separate the rare earths in groups. So you can separate then the middles from the heavies. A further pH-controlled SX process could then separate praseodymium from neodymium. And then we have essentially all the valuables separated from each other, and we can realize most of the value of the rare earths from the lanthanum, praseodymium, neodymium, and the cerium that we removed earlier. The middles and the heavies, one could perhaps still also do that with solvent extraction, but other techniques such as ion exchange, ionic liquids, or chromatography techniques would probably be better, more appropriate to separate them. So it's clear from this separation scheme that processing rare earths is not a simple matter, and it doesn't happen on many places in the world at the moment. This is just a picture of such a rare earth processing plant. It is typical to have trains of hundreds and hundreds of mixer settlers to achieve the separation process. So it's clear that the rare earths are special, and also that they are difficult to separate from each other. So the question is really, where does South Africa stand? Can we separate them from each other? Can we process them? And do we actually have any? And should we actually process them at all? So if you look at the rare earths, for instance, cerium is the 25th most abundant element in the crust, and it's sort of at the level of copper. So clearly they're not very rare, and they also spread very evenly through the crust of the earth. So South Africa certainly should have deposits of rare earths. The most important minerals are bastnaesites, monazites, and xenotime. This is where most of the rare earths are recovered from. But there are also a host of other minor minerals containing rare earths. In South Africa, we have a number of different deposits. We have marine places on the east and west coast. We have monazite deposits that are enriched by alkaline hydrothermal processes, and we have some carbonatites. Then we've also got alkaline igneous rocks like pegmatites in the Naarden-Spruit area. I just want to highlight two specific deposits in South Africa. The monazite apatite quartz deposit at Steenkampskraal. This is small, but it's the richest rare earth deposit in the world. Its ore can range up to 24% rare earths. So it's really unusual deposit in the world. Further deposit that I just want to lift out is the Zandkopsdrift carbonatite deposit. This is the single biggest deposit in South Africa. Extremely difficult to process, but it does contain almost 900,000 tons of contained rare earth oxide. So obviously an important deposit in South Africa. So the further question is, so we've got some rare earths in South Africa, and can we process it in South Africa? This is the other question that we have to ask ourselves. In the first place, I would imagine that although it's difficult to process, South Africa has a large amount of skill in the country with respect to separating elements from each other. For instance, our PGM industry has a complicated process. So I have no doubt that we have the skills in South Africa to be able to design and process rare earths in South Africa. The only problem really is because it's so complex, it also becomes very capital intensive to build such a separation plant. For instance, Molycorp in the US spent about $500 million to build their plant, whereas the Linus plant in Malaysia cost about $500 million Australian dollars. These are all for plants in the region of 20,000 tons per annum of total rare earth oxide production, which is regarded as the economies of scale to be competitive globally. So one can see from this that from a capital perspective, this is enormous. So can South Africa afford to do this? Well, probably not, considering a single deposit, because none of them are really big enough to pay back such an enormous capex investment. So South Africa should, the only solution for this would be to do this in a central fashion, to have a centralized processing and refining facility that will be able to process material from all these deposits. So such a facility would probably look like the following. The mining and physical concentration could probably be done on site at each of these deposits. Then one would have a joint facility to prepare a chemical concentrate by cracking, leaching, and purification, followed by a refinery, and then further down the stream. Now, as one can see, the building blocks for South Africa are all there. We have the rare earths, we have the capability, and we also have a very well-defined regulatory policy with respect to, or framework with respect to radioactive materials, since all these rare earths contain radioactive materials. The question is just the funding, the capital funding of such a process, such a facility. In South Africa, it probably has to be seen as a strategic project, and the government of South Africa would really have to take a strategic view on this, and it is actually important to act as quickly as possible as well, since there's probably a window of 10 more years before, for the next big refinery in the world. So I think it is imperative for South Africa to consider such a concept of centralized rare earth processing, because I believe that's the only way that one can actually establish a competitive production capability in South Africa. So, having said all that, the rare earths are special. They are also difficult. They're also expensive to produce, but I do believe it can happen in South Africa if we can just get all the parties to get together and make this work. So, in conclusion, I would just like to say that rare earths, in my opinion, may be difficult to process, but they really are special, and I believe they hold the key to a better world. Thanks very much.
Thank you, Leon. That was very interesting. My chemistry knowledge has definitely stepped up a few levels since varsity. Thank you for that. And I must say that it gives you an interesting perspective on why it is such a complex process, all the refining and separation of those elements. So from my side, that was very informative. Thank you. We have a few questions, and I think some of them you've actually answered throughout. But here's a few technical questions. Has there been any progress made on processing rare earth silicate minerals such as allanite, and are there mines that produces rare earths from rare earth silicates?
Sorry, Isabel, could you just please repeat that? I didn't quite catch that.
Okay, so the question is, can you see the Q&A? And if you open the tab?
Yes, I can.
Okay, then you can read the question from Oscar van Antwerpen yourself, if it makes it easier. So can you just read it aloud, because for the people to see?
Yes, so if I press answer live, I can answer?
Yes, you can answer.
Okay, there hasn't really been any progress made on progressing of rare earth silicate minerals to date, because the focus has really been on the bastnasites and the monazites. This is where almost all of the rare earths have been produced from now. But there are possibilities. So there are no mines currently producing any rare earths from these silicates, but there are ways to progress them. Mintech, for instance, has developed a really innovative process called Pi-Earth. It's a high temperature process, a smelting process that offers for treating and concentrating such deposits. But my view is currently, I'm not sure if there will be any focus at the moment on such deposits, because from a terrestrial perspective, there are just so much monazites and bastnasites available. And then the other mineral to focus on really is the xenotime, which contains higher proportions of heavy rare earth mineral elements. So I think the short answer there is I'm not aware of any progress made on targeting these type of minerals at all currently.
Okay, thank you. So can you hear me a little bit better now, Leon?
Yes, thanks. Thank you, Isabel.
I
Yes,
up the volume. Okay, so we have also, I think it's very important. A lot of the questions are about the resources. And as you said very well, there are a lot of resources, but a lot of the deposits are quite small. Even in stuff like, if you think about, the question was asked about the ash and byproducts of rare earths, and how much of rare earths are in our byproducts. And I think the answer is very simply put, is that you need a centralized refinery to make it worth your while to process these small byproducts and small deposits, if I can summarize for you. Is that correct?
Yes, Isabel, that certainly is. You know, in order to get any kind of value out of these materials, you have to take it right through to separated rare earth elements, really. And the only way you can do that is if you've got such a processing facility. So I don't think there's any chance that you can realize any value from these materials unless you have a processing facility that can do that.
Yeah, so I think that is one of the big areas that Mintek is currently working on, is to saying it's almost the chicken and egg. If you have a centralized refinery, then the smaller deposit has a chance to actually unlock their value.
Yes, Isabel, that is absolutely correct. There's all the deposits in South Africa could lie dormant if one cannot get them processed right through to separated elements, because this is where the real value lies. In fact, as you move from concentrate to individually separated rare earths, the value essentially increases exponentially. So,
Yes.
so for instance, if you just produce a concentrate, depending on the quality of the concentrate, anything from 10 to 30% of the value is the maximum that you can realize from there. So the rest of the value can only be realized when you process it further and separate it. So, and therefore, you know, that could be the difference between exploiting a deposit or not.
Yeah. So I've got an interesting question for you. Are there potential opportunities to convert existing refineries that are currently idle to eventually treat rare earths? What are the key building blocks a rare earth refinery would require? For instance, the Scorpion zinc refinery in Namibia just got put into care and maintenance.
Yeah, Isabel, I think the big thing is the complexity of the separation. Like I said, the typical separating plants, say in China and elsewhere, have large numbers of mixer settlers, and also if you want to reduce the number of mixer settlers, you have to control the process conditions extremely tightly. For instance, pH control. That will help you to reduce that. But I think it's not a simple matter of just saying, well, we've got some mixer settlers somewhere in the plant, and we can now refine rare earths from there. I think that's probably not necessarily feasible. Although many of the other peripheral equipment would be there, it could be a matter of modifying the setup and retrofitting the equipment that one needs. That's potentially possible. But to use them just as they are, that doesn't seem feasible to me.
Okay. And another interesting one from Quinn, given the massive complexity of the process flow sheets and plants for rare earth refining, do you think there's scope for 4IR technologies such as data science and computational modeling to help with optimization? Or are we really up against the fundamental physical limits of these special metals?
No, I think, Isabel, there are always opportunity. When one has a complicated, in my mind, a complicated flow sheet, you know, the control of such a complicated flow sheet has a lot of potential upside to it. And if one can use such approaches to, you know, to realize all the potential benefits and cost savings and even process improvements, I'm certain that one can do this, especially in a case like a centralized processing situation where you have all these different ores coming in from different places, complicating your flow sheet. Certainly, I think there must be potential for IR to add value to such processing.
Thank you. And here's another question we are going to put you to test. Thank you for the great presentation. My question is regarding the association of rare earths with radioactive material thorium. In terms of the chemistry, how difficult is it to separate thorium from rare earth elements?
Yeah, fortunately, the answer there is it's very easy. It can be done. It can be done very easily, and we have done that at Muntec often. It is very easy to separate the thorium from the rare earths.
Another nice thing. Yes.
You can do that up front, for instance. You can do that by several methods, like precipitation methods up front, or you can separate them up front by a simple SX process like a TBP extraction, for instance. But overall, it's actually relatively simple to separate the uranium and the thorium from the rare earths.
So that has at least some good news.
Yeah.
In terms of, so regarding the valence of the rare earths, can it be used as coagulants? In brackets, expensive, I would imagine, but is it possible?
It has been used, yeah. It has been used, especially the cheaper ones like cerium and lanthanum. So yes, they can.
So another nice question, I think, is, are the environmental standards associated with the Chinese rare earths productions lower than, I think, for example, associated if we have a Western type of plants, which would make our OPEX higher than Chinese?
Absolutely, Isabel. That's been one of the major issues with Chinese production. The standards have been, I think low is possibly quite generous. I've seen pictures of areas around, especially where they recover the rare earths from ionic clays, ion exchange clays. It certainly looks like a moon landscape, and all the waste storage facilities are still sitting there, and really, it's really been a big issue. I know that the Chinese authorities are tightening up tremendously on that, and that has also led to some shortages in the market. This tightening up on the environmental regulations, but up to now, it's really been poor, and certainly the Western standards. No rare earth processing would be able to be done under those circumstances, under those environmental conditions.
Yeah, so I think the question that I thought about in that comes from this question is, if you are a producer, like if you make iPhone and you know there's rare earth elements in your product, you would be willing to pay a little bit more for your metal if it's from a cleaner production site. And I know that these big companies like Apple and those guys are looking at it. buying their metal from environmentally responsible producers. So I think the question is basically, would the markets allow a higher cost if you have a clean production, in your opinion?
Yeah, Isabel, I think possibly not right now, but I certainly think the move is in that direction. It certainly is, and that's why when I spoke about the 10-year window for a next production facility or production capability to come on stream, that is one of the issues that such a facility will have to look at. Not only do you have to be low on the cost scale or competitive on the cost scale, you also have to show that environmental responsibility, because that is certainly something that is moving more and more in that direction. And if one designs such a facility and such a process, that certainly, in my opinion, would be one of the issues that one will have to give serious consideration.
So we're coming back to that centralized refinery, which we are both big proponents of, myself and Leon. The question from Tim Sambrook is, would this kind of centralized refinery be able to cope with all the varied levels of pre-concentration from the mines? I mean, how would the refinery cope with the blended stream variations?
Yeah, Isabel, this has been the topic of much of the work that was done at Mintec over the last 5 or 6 years. Is exactly that, and I think if we take Zandkopsdrift, we take the marine placer deposits on the coast, we take the monazites, the apatites in South Africa, all these streams. We have shown that by doing upfront physical concentration and then a standardized chemical cracking and purification step, it is a great equalizer in that you can then have a consistent feed into your refinery. And we have done a great deal of simulations, taking different levels, different proportions of different sources, and we are confident that such a refinery can handle all these diverse deposits that we find in South Africa. Especially, for instance, one of the big issues that we had was the Zandkopsdrift issue. Zandkopsdrift carbonatite was very difficult, and it probably would have led to some kind of a split stream processing. But with the development of say, the pi earth concentration process for Zandkopsdrift, for instance, that removed that complexity. So indeed, I think with all the work we've done over the last 6 years or so, we are confident that such a refinery can handle this complexity and variability.
We're staying on the centralized refinery. So Anthony says China's hold on these metals is not about to fade away, as evidenced by China's international expansion and the conquest of new resources of rare earths. While the majority of mining projects are dormant given the current price levels, China is making some appearances, particularly in Greenland, and even in the Balkan Dotson Ridge deposit in the United States. Leon, the question to you is, are you aware of any moves by the SA government to invest in a central refinery, or is this merely a pipe dream?
No, I think the Minister of Mining, of Mineral Resources and Energy has actually made some public statements about the support that the government would have for such a development. So I think it's high on the government's list of priorities for development. Like I said, the complication is really the funding, and there are a number of parties that one will have to bring together. But I certainly think it is a stated objective from the South African government to establish not only a production capability in South Africa, but also a downstream beneficiation capability, such as magnets, rare earth magnets, for instance, rare earth chemicals, and also looking at things like medical isotopes from rare earths. So I believe it's high on the list of priorities in the Department of Minerals and Energy.
Yeah, I think that is also where Mintek is playing such a strong role because of our expertise in refining. One of the things about this SACREF centralized refining facility, Leon, is that it probably is a SADC initiative. We're going to have to have concentrate from the entire region to really make it worth our while. Is that correct?
Yeah, Isabel, I think it's probably correct for a number of reasons. I do think we have enough rare earths in South Africa to feed such a facility, but I think given that this is so necessary for exploiting of rare earth deposits, say for instance in the SADC region, it's from a political and economic development perspective. I certainly feel that making such a initiative, a SADC type of initiative, or the Southern African initiative, I mean, this would just make sense. That would allow all these deposits to be exploited, and with the economic benefits that they bring. So I don't believe it should just be a South African thing. It can be, but I don't think it should just be a South African thing.
And also, I think I've heard you before state that there's really only sort of market space for one more big refinery in the next 10 years, and we want to be that one.
Yeah, Isabel, that's not really necessarily only my view. I think it's also the view of Roskill, for instance, study groups like Roskill, for instance, also. In the next 10 years, certainly there's space for another world-class production capability. And obviously, we are not the only ones in the race. But the question that one has to ask, why not South Africa? We have got a lot of things going for us. We have rare earth deposits. We've got a highly developed mining sector. We've got the skills in terms of processing in South Africa. We've got a highly developed nuclear framework, management framework. So, we essentially have all the building blocks. So for me, the question is just, why not South Africa?
Yeah. So in terms of the processing aspect, more technically, is the criticality of pH control. What is the proximity? What would be a best location for such a refinery? Would you need to be close to sulfuric acid and calcium carbonate industrial sources, for example?
Yeah, Isabel, especially if you look at, for instance, your earlier point that perhaps we make it a SADC or a Southern African, that you'd probably want to be at the coast. But I think the big thing any decision on the location of some, and I think that would be the defining thing. What are you going to do?
Yeah, Leon, you may have just to repeat your answer in short. We had a bit of a glitch with the internet connection on your side. Just the location. I heard you say it needs to be near the coast.
Yeah, I think from transportation perspective, it would have to be near the coast, because that is by far the best way to transport concentrate to such a facility. That's the first place. But I think the big thing is probably the handling of the nuclear material, waste material that comes from processing. that has got to be at a in an area where one could store this material, and therefore, you know, the Western Cape near Falpits area, Steenkampskraal as a potential area, because Steenkampskraal is essentially a thorium mine. So we've looked at several locations, and based on this, Saldanha Bay is probably a very good location to have such a facility. So, this area is well developed. The services are there. It is close to the potential storage areas for thorium. It has a harbour. For instance, taking concentrate by ship to Richards Bay or Saldanha, it's not a massive increase in costs. Road transport, on the other hand, you know, does become expensive. But so we think currently, our current thought is probably Saldanha Bay has its nose ahead.
I mean, it is an obvious question, but you do have the challenges of transporting all the different concentrates from different locations to a centralized facility and across borders with radioactivity. What do you think all of that, how, does it make it viable if you have a centralized facility, taking those things into account?
Yeah, the transport of radioactive material obviously is a problem, but there's an established framework for that. It's not the first time that this has happened. There's an established framework. One will just have to abide by this, but I don't necessarily think that will be a game changer in the specifics. I think the financial costs of transporting would be a factor, obviously, of this. That's why I would imagine if one transported material, say from the east coast around to Saldanha Bay, say from Tanzania, from the Wigo Hill mine, for instance, you do this by ship, and I imagine that may be viable. I think one will always have to do the economics on that before you decide, but you know, it is potentially possible.
So the feasibility studies for the SACRIF is primarily based on South African deposits?
At the moment, yes, because you know, we wanted to see whether it has to be established somewhere, and you know, South Africa is the obvious place. So I think what we've done is we've looked at South Africa only, but we've also looked at transporting same material from Tanzania and Malawi, for instance. So we've also included that, and even there, it looks as if it could be viable. But obviously, you know, before you make any kind of investment in that, you'll have to do a proper study on that.
So one of the questions, in fact, is where is the most of rare earth ore from Africa currently that's currently being mined coming from? Is that from Malawi and Tanzania?
None of the ore is actually mined yet. From Burundi, they are mining and hand sorting material in Burundi, for instance. But as far as I know, no rare earth ore is actually mined and processed anywhere from Africa.
Okay, that's interesting. Leon, we've run a little bit out over time, so there's a few more questions, but I'm sure that I think the only sign usually is of a lot of questions is that we should have another session with you, maybe a more panel discussion about rare earths processing and opportunities in South Africa. So I think that is an invitation, a sneaky invitation from me to you already, and I'm sure the attendees, the participants today, I had lots of positive comments, people saying thank you very much for your time and for the insights. And as always, there's going to be a demand for more of your time in the future. But thank you very much. And I think we will call this an end for today just because we've run out of time.
Okay, so well, no problem. And thanks to everybody.